A silent energy revolution is unfolding behind closed laboratory doors. Motionless power generation is poised to dismantle everything we know about electricity. By the end of this exploration, you will understand how these hidden breakthroughs could permanently solve our global energy crisis. We will venture into labs where scientists are capturing power from the empty space around us and transforming ambient heat into usable current. How do you think a world without power cords or fuel shortages would change your daily life? These radical ideas did not appear from nowhere. They emerged from the dreams of brilliant minds who dared to challenge the scientific establishment. Nikola Tesla spent his later years obsessed with a grand vision, a world powered not by wires and coal, but by the Earth's own invisible energy fields. To his contemporaries, it sounded like pure fantasy. For decades, his most ambitious concepts were relegated to the fringes of physics, seen as interesting but ultimately impractical thought experiments. Mainstream science was busy perfecting the machine, building bigger turbines and more efficient engines, all relying on the age-old principles of spinning magnets and burning fuel. The notion of simply pulling power from the silent, empty air seemed like a fool's errand, yet a handful of modern researchers refused to let that dream die. They quietly pored over Tesla's old notes, seeing not madness but a roadmap. Their crucial breakthrough was the realization that Tesla lacked the tools. Today, we have those tools. We have nanomaterials with astonishing properties and a deep understanding of the quantum world, the strange rules that govern the universe at its smallest scales. These allowed scientists to finally build what Tesla could only theorize. They are creating solid-state devices, chips with no moving parts, that can directly convert ambient heat and even the subtle quantum fluctuations of empty space into a steady flow of electric current. This is not merely an improvement on the old way, it is a complete philosophical shift. We are moving from an era of extraction and combustion, of loud, grinding machinery, to an era of silent, direct conversion. How did they achieve this seemingly impossible feat? The answer lies in harnessing the constant, chaotic dance of the universe itself. This constant, chaotic dance of the universe is not random noise, but a symphony of untapped power waiting for the right instruments to play it. At the heart of this silent revolution are three core scientific principles that make motionless generation possible. The first is a bizarre quantum phenomenon called quantum tunneling. In the strange world of the very small, electrons do not always behave like tiny billiard balls. They can, in effect, perform a kind of magic, vanishing through a solid barrier and appearing on the other side without ever having crossed the space in between. This is not a theory, it is a proven fact of quantum mechanics. Scientists are now designing devices that use this ghostly ability. They create incredibly thin barriers that electrons can tunnel through, and by controlling this flow, they capture a tiny electric current directly from the atomic vibrations of the material itself. No motion required, just the inherent energy of atoms at rest. The second principle taps into the subtle pressures all around us. Piezoelectric materials are special crystals or ceramics that generate a small electrical voltage when you squeeze or bend them. Think of it like a microscopic power plant built into the material's very structure. Now, imagine this not from a hard push, but from the gentle, constant vibrations of a building, the hum of a highway, or even the faint tremors in the ground beneath your feet. These materials can transform that ambient mechanical energy we never even notice, into usable electricity. The final piece involves the invisible ocean of energy we are all swimming in. Our world is saturated with electromagnetic fields from radio and television broadcasts, cell phone towers, and Wi-Fi signals. Advanced circuits can now act like microscopic nets, harvesting this ambient radio frequency energy and converting it into direct current. Furthermore, devices called thermoelectric generators can capture power from a simple temperature difference, like the warmth of your hand compared to the cool air, or the heat from a machine versus a room's atmosphere. These methods completely bypass the need for spinning turbines and burning fuel. They offer the promise of nearly limitless efficiency with zero moving parts to wear out or break down. Each of these principles opens a unique door to innovation, and what lies behind those doors are the extraordinary materials that make it all possible. These extraordinary materials are not found in nature. They are born in the sterile silence of advanced laboratories where scientists engineer matter itself. The secret lies in a class of substances known as metamaterials. Think of them as custom-built atoms, arranged in intricate patterns that give them properties impossible for any natural element. A metamaterial can be designed like a perfect trap for ambient energy, bending electromagnetic waves and guiding them into a circuit with almost no loss. It is the ultimate energy net woven from the blueprint up. Alongside them are topological insulators, materials that behave like two substances in one. Their interiors are stubborn insulators, blocking the flow of electricity, but their outer surfaces are flawless conductors, allowing electrons to race along with minimal resistance and virtually no energy wasted as heat. This unique property is a game changer for efficiency. Then there is graphene, a true wonder material. It is a sheet of carbon just one atom thick, yet it is stronger than steel and conducts electricity better than copper. This incredible sensitivity makes it perfect for capturing the faintest whispers of energy, from the smallest temperature shift to the most subtle vibration. Crafting these substances is an art of extreme precision. They are often grown layer by atomic layer in ultra-high vacuum chambers, environments cleaner than any hospital operating room, to ensure that not a single stray atom disrupts their perfect structure. Without these material miracles, the dream of motionless power would remain just a dream. They form the physical heart of the revolution, the silent, solid-state engines that are now being prototyped in hidden workshops around the globe. These material miracles are now taking physical form as working prototypes. In university clean rooms and corporate research hubs, engineers are assembling the first generation of solid-state generators. One of the most promising designs focuses on recapturing waste heat. Enormous amounts of thermal energy are lost every second from factory exhausts, vehicle engines, and even computer servers. A new class of thermoelectric modules is being designed to clamp directly onto these hot surfaces. They contain no fans or fluids, just specialized semiconductor chips that create a voltage when one side is hot and the other is cold. This simple temperature difference drives a silent, continuous flow of electricity, turning waste into a valuable resource right at the source. Another device is learning to listen to the city's heartbeat. Piezoelectric arrays, no larger than a postage stamp, are being embedded into bridges and building frames. They capture the relentless, low-frequency vibrations from traffic and machinery, converting the city's constant hum into enough power to run structural health monitors and environmental sensors indefinitely. This creates a self-powered nervous system for our infrastructure. Then there are the most speculative frontiers. In a handful of highly secure labs, quantum energy harvesters are being tested. These circuits are engineered to interact with the quantum vacuum, the seething sea of zero-point energy that exists even in absolute emptiness. While this field remains intensely experimental and controversial, early results suggest it might be possible to coax a tiny, usable current from the fabric of space itself. Each of these prototypes serves a different master, from industrial waste to urban vibration to the quantum void, but they all share one revolutionary trait: an utter lack of moving parts. Their silent, steadfast operation is not a laboratory curiosity. It is being proven in the most demanding environments on Earth. The silence inside these testing chambers is so profound it becomes a sound of its own. To prove that a device can pull power from nothing, you must first create a perfect nothing for it to operate within. This is the purpose of the echoic chamber. Its walls, ceiling, and floor are covered in jagged, sound-absorbing foam, but they also block another kind of noise, the constant barrage of electromagnetic signals from our Wi-Fi, our phones, and our broadcast towers. Inside this room, scientists can finally hear the faint whisper of a device harvesting energy from the ambient fields that remain, measuring its true potential without any static from the modern world. Even the slightest tremor can ruin an experiment. That is why the most sensitive prototypes rest on ultra-low vibration platforms, massive tables floating on cushions of air or magnetic fields. These platforms isolate the device from the subtle rumble of a truck driving by miles away, or the vibrations of footsteps in the hallway. They ensure that every microvolt of electricity generated comes solely from the intended source, be it a thermal gradient or a quantum fluctuation, and not from the mundane shaking of the Earth. For the most exotic research, scientists must also eliminate the jiggling of atoms themselves, which is the very nature of heat. They achieve this by placing components inside cryogenic systems, cooling them to temperatures within a few degrees of absolute zero. At these frigid extremes, the normal thermal vibrations of atoms almost completely stop, allowing the bizarre, delicate effects of quantum mechanics to take center stage. Only under these hyper-controlled conditions can researchers validate whether a new generator is truly efficient and scalable. It is here, in this engineered void, that the science fiction of yesterday earns the credentials to become the foundational technology of tomorrow. The journey from a sterile laboratory chamber to the chaotic real world is the ultimate test for any new technology. These motionless generators face a gauntlet of challenges before they can truly change our lives. One of the most significant hurdles is their current energy density. The power output of today's prototypes is often measured in microwatts or milliwatts. This is more than enough to run a tiny environmental sensor or a low-power microchip, but it falls far short of what is needed to charge a phone, power a home, or support a section of the electrical grid. We are, in essence, learning to capture the whisper of energy when we need to hear a shout. This limitation pushes material scientists to their limits, demanding new compounds and structures that can harvest vastly more power from the same ambient sources without increasing the device's size. Beyond raw power, these devices must prove they are tough. A laboratory is a controlled, gentle environment. The outside world is not. A generator designed to sit on a desert highway must endure blistering heat by day and freezing temperatures at night, all while resisting corrosion from dust and salt. A unit embedded in a bridge must withstand decades of vibration, torrential rain, and the physical stress of the structure itself. Even a simple indoor device must operate reliably for years without maintenance, its delicate internal nanostructures protected from humidity and everyday wear. A failure in any one of these areas could render the entire technology useless for widespread deployment. Then comes the complex puzzle of integration. Our existing power grid is a monumental machine built for a specific kind of energy, one that flows in predictable, alternating currents from massive, centralized sources. Motionless generators, by contrast, often produce direct current in small, decentralized amounts, and their output can fluctuate with ambient conditions. How do you connect millions of these tiny, variable power sources to a grid designed for a few thousand giant, steady ones? It would require a complete rethinking of grid management, new types of power converters, and smart systems that can balance this new, diffuse form of energy with traditional supplies. This is not just a technical upgrade, it is a logistical and economic revolution. Overcoming these obstacles is not a single task, but a multi-front war being fought by researchers and engineers who are convinced the prize is worth the struggle. So how do we amplify that quiet whisper into a powerful voice? The first strategic approach is a dramatic push to enhance energy density, the amount of power squeezed from every cubic centimeter of these devices. The key lies in manipulating matter at an almost impossibly small scale through nanostructuring. Scientists are no longer working with flat, smooth surfaces. Instead, they engineer materials with intricate forests of microscopic pillars, pores, and wires. This nanoscale terrain dramatically increases the surface area available to capture ambient energy, much like how a sponge holds vastly more water than a flat tile. A device no larger than a fingernail can be given the effective capture area of a dinner plate, all without changing its physical footprint. This is just the beginning. To capture the chaotic mix of energy in any environment, researchers are building multi-layer generators. Imagine a single chip that acts like a multi-tool. Its top layer might be a thermoelectric material harvesting power from the heat radiating from a car engine. Just beneath it, a piezoelectric layer soaks up the vibrations from the engine's rumble. And below that, an electromagnetic layer could capture stray radio frequencies from the vehicle's own electronics. This simultaneous, stacked harvesting means the device is never reliant on a single energy source, dramatically boosting its total output and reliability. Perhaps the most transformative element being integrated is superconducting materials. Unlike ordinary wires that resist electrical flow and waste power as heat, superconductors offer a pathway of zero resistance. While the challenge of achieving room temperature superconductivity remains, even current high-temperature variants could revolutionize these systems. They could be used to create incredibly efficient loops to store minute pulses of harvested energy, building it up until there is enough to be released in a useful burst, all with almost no loss. This combination of increased capture area, multi-source harvesting, and near-perfect efficiency is the formula that could finally make motionless generators competitive. It is the engineering pathway that could one day see a panel on your roof capturing power from sunlight, wind vibrations, and temperature differences all at once, or an electric car that partially powers its own systems from the heat and motion of its own journey. While boosting power output is one critical battle, ensuring these silent generators can survive the real world is another. The second strategic approach focuses on building near-indestructible environmental resilience. Picture a motionless generator mounted under a desert highway, baking in relentless sun one moment and chilled by cold desert air the next, or one embedded deep within the steel and concrete of a skyscraper, vibrating constantly for decades. These are not gentle environments. To endure them, laboratories are creating advanced protective armor for these delicate devices. The first line of defense is a suite of specialized polymer coatings, applied in layers thinner than a human hair. These transparent shields are engineered to be incredibly hydrophobic, meaning water literally beads up and rolls off, carrying dust and corrosive salts with it. This prevents moisture from ever penetrating the sensitive nanoscale structures inside, a primary cause of failure in electronics. For even harsher conditions, scientists are turning to composite materials. By embedding the active energy harvesting elements within a matrix of carbon fibers or fine ceramic powders, they create a material that is both tough and functional. This is like suspending a fragile crystal in a block of ultra-strong, flexible glass. The composite provides the structural strength to withstand physical shocks and constant vibration, while its carefully tuned composition allows thermal energy or electromagnetic waves to pass through to the core components with minimal loss. The ultimate goal in this field is autonomy, creating materials that can heal themselves. A few research teams have prototypes that use microcapsules filled with a liquid healing agent dispersed throughout the material. If a tiny crack forms, these capsules rupture and release the fluid, which hardens to seal the breach, much like a scab forming on a cut. This self-repairing capability could extend the operational lifespan of a generator from years to decades, making it a truly set-and-forget technology. This intense focus on durability is not just about making devices last longer. It is about enabling their deployment in the most remote or hostile places on Earth, from the deep sea to the Arctic tundra, where sending a repair crew is simply not an option. But building a tough, independent generator is only half the solution. The true potential of this technology emerges when it learns to communicate and collaborate with the other smart systems around it. This final strategic approach weaves these silent generators directly into the fabric of our existing energy systems. The future is not about a single winner, but about creating robust hybrid networks. Imagine a standard solar panel, already a marvel of direct energy conversion. Now picture it transformed. Its aluminum frame is no longer just a passive support structure. It is embedded with thin, flexible piezoelectric strips that gently flex with every gust of wind, generating a small but steady stream of power from the very air moving around the panel. This vibrational energy is captured alongside the sunlight, supplementing the total output even during cloudy periods when solar generation dips. Simultaneously, on the back of the solar cell, where the sun's rays create significant waste heat, a grid of thermoelectric modules goes to work. These solid-state chips exploit the temperature difference between the hot panel surface and the cooler ambient air, converting that otherwise lost thermal energy into yet more electricity. This creates a triple-threat energy harvester, capturing power from light, motion, and heat all at once from a single installation. The beauty of this hybrid model is its inherent resilience. On a calm, sunny day, the solar cells dominate. On a windy, overcast day, the piezoelectric elements take a larger share. The system is constantly balancing itself, leveraging the strengths of each technology to smooth out the peaks and valleys that plague single-source renewables. This synergistic approach makes the entire energy system more reliable and efficient, a practical and immediately applicable step that bridges our current infrastructure with the silent energy future. These are not just theoretical concepts, they are already being tested in the field with remarkable results. Beneath the feet of thousands of daily commuters, a quiet revolution is already generating power. In a pilot project at a major subway station, the very act of walking was transformed into a source of electricity. Specialized tiles, crafted from advanced composite materials, were installed across the busiest thoroughfares. With every footstep, these tiles experienced a minute flex, a tiny mechanical stress that their embedded piezoelectric elements instantly converted into a small electric current. It was not a single large jolt of power, but a continuous, gentle rain of energy contributions from the crowd. This collective effort was harvested and channeled to power the station's LED lighting and real-time information displays, directly offsetting a portion of the station's energy draw from the conventional grid. The true genius of the system lay in its complete lack of moving parts. There were no gears to grind, no turbines to spin, and no audible hum. Commuters experienced no change in their routine, unaware they were participating in a small-scale power plant with every step they took. The data collected over months told a compelling story. During the morning and evening rush hours, when foot traffic was at its peak, the station's reliance on the main power grid dropped significantly. This was not a laboratory simulation, it was a real-world demonstration of scalability, proving that the more a public space is used, the more power it can potentially provide. This seamless integration into the urban landscape offers a powerful blueprint for the future. It suggests that our cities themselves, from their sidewalks and parks to their sports stadiums and shopping malls, could be reimagined as active, productive components of our energy infrastructure. This success in a public space naturally sparks a question: how will this silent energy transition begin to touch our personal lives, right inside our own homes? The harsh Arctic silence is now broken only by the soft hum of data. In this frozen landscape, where the sun vanishes for months and temperatures plunge to levels that shatter steel, traditional power has always been a fragile lifeline. Solar panels sit useless under the perpetual night, and fueling generators is a dangerous, costly, and often impossible task. Yet, critical climate science depends on continuous data from these very places. The solution arrived not with a roar, but with a silent conversion. Scientists deployed networks of environmental sensors powered exclusively by motionless thermoelectric generators. These solid-state devices perform a simple yet profound trick. They are planted so that one side makes contact with the relatively stable, deep cold of the ice, while the other side is exposed to the frigid air. Even the slight temperature difference between the frozen ground and the slightly warmer atmosphere is enough. The generator harvests that thermal gradient, converting it directly into the tiny amount of electricity needed to run temperature, humidity, and atmospheric sensors. There are no moving parts to freeze solid, no batteries to drain and become toxic waste in a pristine environment. They simply sit, embedded in the ice, turning the cold itself into a constant, reliable power source. These units have now operated autonomously for years, surviving blizzards and the crushing cold that would incapacitate any mechanical system. They provide an unbroken stream of information on permafrost thaw and atmospheric changes, data that is vital for understanding our global climate. The profound lesson from the Arctic is not just about surviving extreme conditions, it is about perfect reliability in total isolation. This same principle of harvesting energy from the body's own internal environment is now guiding a revolution in a far more personal frontier, the world of medicine. Deep inside the human body, a new kind of power plant is being born. The same principles that draw energy from a cold Arctic wind are now being adapted to run on the warmth of your own blood. In laboratories focused on medical miracles, researchers are creating the ultimate autonomous devices, motionless generators small enough to be implanted and powered by the body itself. For patients with pacemakers or deep brain stimulators, this represents a profound liberation. These life-saving devices currently rely on internal batteries that last 5 to 10 years, after which a patient must undergo another invasive and risky surgery for replacement. The new goal is to create a device that never needs a battery change, drawing all the power it requires from its biological environment. One of the most elegant solutions taps into the body's constant thermal output. A tiny thermoelectric chip, smaller than a postage stamp, can be implanted just beneath the skin. One side of the chip is warmed by the body's internal heat, around 37 degrees Celsius, while the other side is cooled by the skin's surface exposure to the cooler air outside. That small but steady temperature difference is all it takes to generate a continuous trickle of electricity, perfectly sufficient to run a modern, ultra-low power pacemaker. The device becomes a permanent, self-sustaining part of the person, powered by their own life force. Even more remarkable are the generators that run on fuel already coursing through our veins. A pioneering team has developed a prototype that acts like a biological fuel cell. It uses the glucose abundant in blood as its power source. Specialized enzymes on the device's surface act as catalysts, triggering a chemical reaction that breaks down the sugar molecules. This reaction releases electrons, which are then captured to form a small, constant electric current. It is a device that literally feeds on blood sugar to produce the electricity that keeps a heart beating steadily. The implications for patient safety and quality of life are immense. No more battery replacement surgeries means no more surgical scars, no more risk of infection from repeated procedures, and a significant reduction in both medical costs and personal anxiety. But the path to a safe and reliable implant is paved with immense challenges. Biocompatibility is the absolute priority. The materials used cannot be toxic, cannot trigger an immune response, and must not corrode or degrade inside the body's salty, humid environment over decades. Scientists are experimenting with incredibly inert coatings, like specific forms of titanium, nitride, or diamond like carbon, which the body is far less likely to reject. The generator's entire structure must be hermetically sealed to prevent any leakage of materials into the body or bodily fluids into the electronics. Long-term reliability testing is underway to ensure these silent power plants can function flawlessly for 50 years or more, becoming as dependable as a healthy heart valve. This progress is not confined to the sterile world of medicine. The same drive for autonomy is quietly reshaping the devices we carry in our pockets every day. The same principles powering medical implants are now finding their way into the technology in your pocket. Your smartphone, a device you constantly touch and speak into, is a reservoir of untapped kinetic energy. Prototypes now in development feature an almost invisible piezoelectric film layered directly beneath the screen. Every time you tap an icon or scroll through a feed, that minor mechanical pressure is converted into a tiny pulse of electricity, feeding directly back into the battery. Simultaneously, another element captures the subtle vibrations from your voice during calls, harvesting energy from the sound waves that would otherwise dissipate into the air. While not yet enough to fully power the device, this constant trickle of reclaimed energy can significantly extend the time between charges, turning your most common interactions into a source of supplemental power. On your wrist, a similar quiet revolution is underway. The next generation of smartwatches and fitness trackers are being engineered with thin, flexible thermoelectric bands that make direct contact with your skin. They exploit the simple, constant fact that your body is warmer than the surrounding air. This temperature differential drives a small but steady current, generating enough power to handle background tasks like heart rate monitoring and step counting, reducing the device's drain on its main battery. For simpler Internet of Things devices, like moisture sensors for your plants or location tags for your keys, this could mean a future entirely free of batteries. They would simply draw the minuscule power they need from ambient room heat or subtle household vibrations, operating for decades without any maintenance. This shift offers a profound dual benefit: immense convenience for the user and a major step toward sustainability. By drastically reducing how often we need to plug in or replace batteries, we cut down on both electronic waste and the massive energy drawn from charging billions of devices daily. This growing demand from the consumer electronics industry is not just a market trend, it is a powerful engine for discovery. The push for smaller, more efficient, and cheaper energy harvesters is funneling unprecedented resources and brainpower into the very laboratories where this science was born, creating a virtuous cycle where commercial success fuels even more radical breakthroughs. The economic landscape of energy is poised for its greatest transformation in over a century. The silent, continuous operation of motionless generators directly attacks the core costs that have defined power for generations. Fuel becomes irrelevant, a line item that simply vanishes from the balance sheet. The constant, expensive cycle of maintenance for turbines, bearings, and other moving parts is rendered obsolete by solid-state devices that can operate for decades with no wear. The very architecture of our power infrastructure, a sprawling and vulnerable network of wires and substations, could begin to shrink as localized generation takes root. This is not a marginal improvement in efficiency. It is a fundamental rewrite of the economics of electricity. Industries that live and die by reliability in remote locations are watching this revolution with intense interest. For telecommunications companies, a motionless generator could power a remote cell tower indefinitely, eliminating the logistical nightmare and extreme cost of regularly delivering diesel fuel to a mountaintop. In defense and security, the implications are even more profound. Networks of autonomous sensors could be scattered across a border or a disaster zone, silently monitoring for years without ever needing a battery swap or a fuel run, creating a persistent, undetectable awareness. This radical shift in capability will inevitably give rise to entirely new business models. We may see the rise of energy as a service where you do not buy a generator, you simply lease its constant, silent output. A company could install a series of these devices in your building's framework, and you would pay for the power they produce with no upfront capital cost and a guarantee of perpetual, maintenance-free operation. This transition will be a powerful engine for job creation, demanding a new workforce of material scientists, quantum engineers, and high-tech manufacturing specialists. Yet, this progress will not be without its dislocations. Traditional roles in fuel extraction, power plant operation, and grid maintenance will face inevitable pressure, demanding a societal focus on retraining and economic adaptation. For investors and policymakers, understanding this tidal shift is no longer a speculative exercise. It is an urgent necessity. The flow of capital and the design of regulations must align with this new, decentralized reality. Yet, beyond the balance sheets and market dynamics, the most profound impact of this quiet revolution may be written not in ledgers, but on the planet itself. The environmental footprint of this silent energy is as minimal as its sound. Motionless generators produce absolutely no emissions during their operational life, creating power without a single puff of smoke or a drop of combustion waste. This fundamental shift from burning fuel to direct conversion offers a powerful tool in the global fight against climate change. By harvesting energy that already exists in our surroundings, these devices directly reduce our dependence on fossil fuels and slash the associated greenhouse gas emissions that are warming our planet. But the sustainability story does not end once the device is switched on. The very process of creating these generators is undergoing a green transformation. Inside forward-thinking laboratories, scientists are moving beyond traditional manufacturing. They are pioneering the use of recyclable polymers and biodegradable composites for device casings. They are experimenting with green chemistry techniques, using water-based solvents and low-energy processes to assemble the delicate nanostructures inside, minimizing the toxic byproducts and high-energy costs typically associated with advanced electronics production. This cradle-to-grave commitment to sustainability extends to their deployment in the world's most fragile places. Imagine a network of sensors monitoring the health of a rainforest canopy. A traditional generator would be unthinkable, its noise and vibration scattering wildlife and disrupting the ecosystem. A motionless generator, however, can be placed directly on a tree branch. It sits in perfect silence, harvesting power from the gentle sway of the wind and the subtle temperature shifts between day and night, all while the birds and insects around it remain completely undisturbed. This seamless coexistence with nature is perhaps one of its most profound advantages. By aligning so perfectly with our most urgent environmental goals, this technology does more than just provide power. It actively helps preserve the natural world for generations to come, turning our built environment into a source of clean, silent, and restorative energy. This invisible network of silent power cannot simply be unleashed without rules. As motionless generators move from the lab into our homes and cities, a new framework of regulations is emerging to ensure their safety and reliability. The very nature of harvesting ambient energy raises unique questions. A device designed to capture electromagnetic waves could, if poorly designed, become a source of interference itself, disrupting critical communications like emergency radio bands or the precise signals used by aircraft. To prevent this, international standards bodies are defining strict limits on electromagnetic emissions, forcing engineers to design harvesters that are not just efficient, but also radio-quiet and well-behaved neighbors in the crowded spectrum. Another critical focus is material safety. The advanced nanomaterials at the heart of these devices, while incredibly effective, must be proven safe for long-term human exposure. Regulators are demanding extensive biocompatibility testing, especially for consumer products. They need to know that if a device is embedded in a wall or worn on the skin, no toxic particles can leach out over years of use, even if the casing is scratched or damaged. This has pushed labs to pioneer new, non-toxic alternatives to materials like lead-based piezoelectrics, replacing them with safer, high-performance composites. The ultimate goal is to build a foundation of public trust. A single incident of interference or a health scare could stall the entire industry for years. That is why compliance is not seen as a barrier, but as a necessary step for market acceptance. Independent certification labs are now being established to put prototype generators through a brutal gauntlet of tests, simulating decades of use in just months, verifying that they are as safe as they are silent. This careful, deliberate process ensures that when these technologies finally arrive in our daily lives, they bring only power, not problems. With these essential guardrails being put in place, the path is now clear for researchers to pursue the most radical ideas at the very edge of physics. Beyond the carefully regulated world of commercial prototypes lies a frontier where physics itself seems to bend. A handful of laboratories are daring to probe the quantum vacuum, the seething sea of energy that underlies the very fabric of space. This is not about capturing ambient heat or vibrations, but about attempting to draw power from what appears to be perfect emptiness. The theoretical foundation for this stems from a cornerstone of quantum mechanics, the Heisenberg uncertainty principle. This principle dictates that even in a vacuum at a temperature of absolute zero, fields cannot remain perfectly still. They undergo constant, fleeting fluctuations, a kind of quantum fizz with energy that pops in and out of existence. The goal of quantum energy harvesting is to somehow capture and rectify these infinitesimal bursts into a usable, direct current. One of the primary experimental setups involves creating structures known as Casimir cavities. These are not cavernous rooms, but microscopic gaps between two perfectly smooth, parallel plates placed incredibly close together, often just nanometers apart. At this scale, the quantum fluctuations of the vacuum outside the gap are different from those permitted inside it. This creates a subtle pressure, a force that actually pushes the plates together. Researchers are engineering circuits that attempt to harness this dynamic, to convert the energy of these quantum forces into electricity. Other experiments employ superconducting circuits cooled to near absolute zero. In this frigid, quiet state, shielded from most thermal noise, these circuits become exquisitely sensitive to the vacuum's faint whispers. The idea is to design a circuit that interacts with the quantum field in a way that allows it to absorb a tiny amount of energy from these vacuum fluctuations, effectively charging itself from empty space. The energy levels involved are almost unimaginably small, often quadrillionths of a watt, making detection and utilization a monumental challenge. This field remains intensely controversial. Skeptics point to the bedrock laws of thermodynamics, arguing that you cannot extract useful work from a system in equilibrium at a single temperature, which they contend the quantum vacuum is. Proponents, however, believe that our understanding of these laws is incomplete at the quantum scale. They suggest that cleverly designed non-equilibrium systems, or exploiting quantum loopholes like entanglement, could make the impossible possible. They see the vacuum not as a placid lake, but as a turbulent ocean of potential, if only we learn to sail it. This research represents the absolute outer limit of motionless power, a direct challenge to our most fundamental concepts of energy. The mere possibility forces us to ask a profound question. If we could one day tap the quantum vacuum, what responsibilities would come with a technology that treats the fabric of space itself as a power source? The same silence that makes these generators so promising also cloaks profound ethical questions. Who truly controls a power source that is invisible, ubiquitous, and potentially permanent? The architecture of our energy future is being drafted now in patent offices and corporate boardrooms, raising the specter of a new kind of divide. If the core technologies for harvesting ambient energy become locked behind impenetrable walls of intellectual property and high cost, we risk creating a world of energy haves and have-nots. Affluent communities could become self-powered, their buildings and infrastructure humming with silent, free energy, while less developed regions remain shackled to expensive, imported fuels. This would not merely maintain existing inequalities, it would engineer them directly into the physical environment, creating a chasm between the energy-rich and the energy-poor that could prove impossible to cross. This concern extends beyond simple access into the realm of privacy and autonomy. An always-on energy harvester is by its nature a device that is always listening to its environment. The same piezoelectric film that powers a smart city sidewalk by sensing footsteps could also map the movement of every individual across a public square. The electromagnetic harvester pulling power from the air could be designed to also intercept data from passing devices. When the infrastructure around you is not just powered by, but is made of countless invisible sensors, the potential for a pervasive, inescapable surveillance network becomes terrifyingly real. Who owns the data harvested by the pavement you walk on, or the vibrations from your car? Without clear boundaries, the promise of free energy could subtly morph into a system of total control. Navigating this ethical minefield requires a new kind of compass, one built on a foundation of proactive and inclusive governance. We cannot wait for these technologies to become widespread before deciding how they should be used. Ethical frameworks must be established now, guiding principles that prioritize open standards, mandatory licensing for critical applications, and strict data privacy protections. These frameworks should be forged in collaboration with a wide spectrum of voices, not just engineers and CEOs, but also urban planners, sociologists, human rights advocates, and representatives from communities that have historically been excluded from technological booms. The goal is to bake equity and transparency directly into the blueprint of this new energy layer. The ultimate success of motionless power will not be measured in megawatts alone, but in its ability to empower every single person it touches. This global race for silent power is not a solitary sprint, but a carefully choreographed relay. Behind the secure doors of these laboratories, fierce competitors are also quiet partners. A university team in Europe might possess a groundbreaking theory on quantum tunneling, while a corporate lab in Asia has perfected the nanoscale manufacturing process to test it. Separately, they hit a wall, but together they can run. They connect through encrypted channels, sharing just enough data and theoretical models to advance the work, while legal teams meticulously ring-fence the resulting intellectual property with non-disclosure agreements that are more complex than the devices themselves. Government agencies often act as the unseen facilitators of these alliances, providing funding and high-level security clearance. They recognize that the nation that masters this energy transition will wield immense geopolitical influence, yet they also understand that no single country holds all the pieces to the puzzle. This creates a delicate dance of mutual need, where rivals must cooperate to outpace everyone else. The shared goal of a sustainable future becomes a powerful, unifying force that can, at least temporarily, bridge even the deepest political divides. This intricate web of collaboration demonstrates that the greatest challenges of our time cannot be solved in isolation, but require a new model of innovation, one built on both trust and fierce, protected ambition. The timeline for this quiet takeover is already being drafted by leading research institutions. Experts analyzing the current pace of innovation suggest that motionless power generation will likely become a commercial reality for niche applications within the next 5 to 10 years. The very first devices to benefit will be those where the value of autonomy is highest and the power demands are lowest. Think of the vast networks of Internet of Things sensors monitoring inventory in warehouses or soil conditions on farms. These units could soon shed their batteries forever, drawing all the power they need from the ambient warmth and vibrations of their surroundings. In medicine, the next generation of implantable neurostimulators and pacemakers are already in development with integrated thermoelectric harvesters, aiming for clinical trials within this window. Their promise is a lifetime of operation without a single replacement surgery. For these technologies to move from powering a single sensor to supporting an entire home or business, the timeline stretches further, likely 2 to 3 decades. The primary hurdles are energy density and cost. While a milliwatt is sufficient for a tiny sensor, a household appliance requires watts, a 1,000-fold increase. Achieving this demands not just incremental improvements, but entirely new material discoveries and manufacturing techniques that are still in their infancy. Grid-scale applications where these silent generators would feed power directly into our existing infrastructure represent the final frontier. This will require a complete re-engineering of the grid itself to handle millions of decentralized, variable power sources, a monumental task of both technology and policy. Yet, some of the most ambitious visionaries look beyond these hurdles. They envision a future where the surfaces of our cities themselves become active power generators. Building facades could be coated with energy-harvesting metamaterials that soak up ambient radio waves, while roadways and bridges are laced with piezoelectric composites that turn the relentless pulse of urban life into a foundational power supply. This would fundamentally alter our relationship with electricity, transforming it from a build commodity delivered from afar into a ubiquitous, ambient utility, as freely available as the air we breathe. These projections, however, are maps drawn with today's knowledge. The true journey of innovation is often punctuated by sudden, unexpected breakthroughs. A lab in Zurich or Tokyo could tomorrow announce a new superconducting material that operates at room temperature, or a novel quantum heterostructure that doubles energy density overnight. Such a discovery would shatter these cautious timelines, accelerating the future by decades. This inherent unpredictability is precisely why a continuous, unwavering investment in fundamental research and education is so critical. The engineers and physicists who will unlock these doors are in university lecture halls right now, and the tools they need are being built in today's laboratories. The speed of this silent revolution depends not on a single eureka moment, but on a sustained global commitment to pushing the boundaries of the possible. The financial engines powering this silent revolution are now roaring to life. Venture capital firms known for their high-risk, high-reward bets on the future are placing massive wagers on advanced material startups. They are not just funding companies, they are funding potential paradigms, betting that the startup working on a new piezoelectric polymer today could become the standard for urban infrastructure tomorrow. Some of these specialized energy harvesting firms have already achieved unicorn status, valued at over $1 billion, despite having no physical product on the market. Their worth is locked entirely in their intellectual property, in patents for a novel nanomaterial or a unique quantum circuit design that promises to double energy density. This private sector frenzy is matched by sober, strategic investment from governments. National laboratories, with their decades-long horizons, are receiving substantial grants focused squarely on energy security and technological supremacy. The goal is not merely a better battery, but a foundational energy technology that could render entire classes of foreign energy imports obsolete. This creates a powerful, multi-layered funding ecosystem. On one end, you have agile startups chasing radical breakthroughs with venture capital rocket fuel. On the other, you have the deep, patient capital of state-backed institutions pursuing incremental but guaranteed progress. In the middle, forming a crucial bridge, are the world's largest corporations. Tech giants and industrial titans are not sitting idle. They are forming strategic alliances with top university labs, funding long-term research in exchange for a first look at the results and the talent that produces them. A single corporate research and development division might be exploring a dozen different approaches at once, from thermoelectric coatings for consumer electronics to large-scale piezoelectric systems for smart cities. This diverse financial landscape is the greatest strength of the movement. It ensures that no single idea holds a monopoly on hope. While one team perfects a slightly more efficient version of today's technology, another is funded to pursue a concept that looks more like science fiction. This parallel exploration of multiple pathways dramatically accelerates the entire field, creating a fertile ground for both evolutionary improvements and revolutionary leaps. The sheer scale of this financial commitment reveals a stark truth. The world's most powerful investors and nations are no longer betting on if motionless power will arrive, but on who will control it when it does. The future of silent energy is being written not only in laboratories but also in university lecture halls. For the next generation of innovators, the path begins with a deep foundation in the core sciences that underpin this revolution. A degree in materials science offers the key to understanding and engineering the metamaterials and piezoelectrics at the heart of these devices. Quantum physics provides the theoretical roadmap for navigating the bizarre rules that govern energy harvesting at the atomic scale. Electrical engineering translates these principles into the practical circuits and systems that can manage and distribute the harvested power. These fields are no longer separate silos of knowledge. They are converging into a new interdisciplinary frontier. In response, forward-thinking universities are rolling out specialized courses with titles like Solid-State Energy Harvesting and Physics of Ambient Power. These are not dry academic exercises. They are dynamic workshops developed in close partnership with the very corporations racing to commercialize the technology. Students find themselves working with real-world specifications, designing prototypes for specific industrial problems, like a generator that can power a sensor on a deep-sea pipeline or inside a jet engine. This direct link to industry ensures that the curriculum remains on the cutting edge, preparing students not for the jobs of yesterday, but for the challenges of tomorrow. The most crucial part of this education often happens outside the classroom walls. Internships at national labs and corporate research and development centers provide an invaluable bridge between theory and practice. Here, an aspiring engineer might spend a summer learning to operate a molecular beam epitaxy machine, growing perfect atomic layers for a new thermoelectric material. Another might be tasked with running a prototype through a brutal environmental stress test, subjecting it to simulated decades of vibration and thermal cycling in a matter of weeks. This hands-on experience in prototyping and validation is where abstract concepts become tangible skills. For those outside the traditional university system, the doors to this knowledge are still open. Online learning platforms now host detailed courses on nanofabrication, quantum mechanics, and circuit design, often taught by leading researchers in the field. Open-source communities have sprung up around low-cost energy harvesting kits, allowing enthusiastic self-learners to build their own simple piezoelectric generators or radio frequency harvesters at home. This democratization of knowledge is vital for cultivating a truly global and diverse talent pool. We need not just brilliant theorists, but also practical problem solvers, creative designers, and ethical thinkers. The ultimate goal is to build a community of minds with expertise that spans from the most abstract quantum equations to the gritty realities of mass manufacturing and real-world deployment. The complex limitations facing motionless power today, from boosting energy density to ensuring long-term durability, will not be solved by a single discipline working in isolation. They demand this collaborative, multifaceted approach. The students tinkering in university labs today will be the ones who unlock the full potential of this technology tomorrow, turning today's quiet prototypes into the silent, beating heart of our energy future. A persistent whisper of skepticism follows this technology, rooted in a fundamental misunderstanding. Many hear about pulling power from empty space and immediately cry foul, convinced it must break the sacred law of energy conservation. The truth is far more elegant. These devices are not magic boxes creating energy from nothing. They are exquisitely efficient translators, converting energy that already exists in one form into another, more useful form. They draw from the ambient thermal bath of our environment, from the kinetic energy of vibrations, or from the electromagnetic soup we are all immersed in. The first law of thermodynamics remains unbroken. Energy is neither created nor destroyed, only transformed. Another common misconception is the dream of unlimited, completely free power. While the fuel source is free, the device itself is not. There is a real cost in the advanced materials, the precision manufacturing, and the sophisticated electronics required to capture and condition this diffuse energy. The power is not free, but its fuel bill is zero. This distinction is crucial for a realistic view of its economic potential. Critics often point to the low power output of current prototypes as proof of its impracticality, asking why we would bother with microwatts when the world needs megawatts. This critique misses the point entirely. It is like dismissing the invention of the transistor because its first use was in a hearing aid, not a supercomputer. The immediate and transformative potential of motionless power lies in the vast universe of low-energy applications. Imagine billions of Internet of Things sensors monitoring everything from bridge integrity to soil moisture, all operating for decades without a single battery change. Envision medical implants that never require replacement surgery. These are not niche markets, they are the foundation of a smarter, more connected, and healthier world. This gap between perception and reality is the single greatest barrier to widespread adoption. Overhyped claims from enthusiasts can create a boom and bust cycle of excitement and disappointment, damaging the credibility of the entire field. That is why the researchers driving this revolution are now prioritizing radical transparency. They are openly sharing performance data, discussing limitations alongside breakthroughs, and clearly outlining the long road from laboratory prototype to a product on a store shelf. This honest communication builds a foundation of trust, replacing fantastical dreams with a solid, achievable vision. The goal is to foster a public conversation based not on science fiction, but on the exciting and very real science that is quietly unfolding. The blueprint for this silent revolution is not found in a single textbook, but scattered across many. It thrives on a powerful synergy between disciplines that were once considered entirely separate. Nanotechnology provides the essential tools, allowing scientists to act as atomic architects. They can now assemble materials one layer of atoms at a time, creating intricate nanostructures with vast surface areas perfectly tailored to capture ambient energy. This precise control at the smallest possible scale is what pushes energy conversion efficiency to levels once thought unreachable. Simultaneously, bioengineering offers a deep well of inspiration drawn from billions of years of evolution. Researchers are not just building machines, they are mimicking life itself. They study the elegant efficiency of enzymes, the biological catalysts that power every cell in your body. By understanding how these natural molecules facilitate energy-producing reactions at room temperature, scientists can design synthetic counterparts to do the same, creating devices that essentially metabolize their environment for power. This biological approach leads to generators that are not only highly efficient but also biocompatible, able to function safely within the human body or in delicate ecosystems. Yet, designing these complex systems is a puzzle with near-infinite variables. This is where data science enters the lab. Machine learning algorithms can process immense datasets from prototype testing, identifying patterns invisible to the human eye. They can run through millions of simulated configurations for a piezoelectric crystal lattice or a thermoelectric heterostructure, predicting which atomic arrangement will yield the highest power output under specific environmental conditions. This computational guidance dramatically shortens the development cycle, turning a process that once took years of trial and error into a matter of weeks. The fusion of these fields creates a research landscape richer and more resilient than any single specialty could achieve alone. A nanomaterials expert might design a superb structure, but a bioengineer can suggest a coating that prevents the body from rejecting it. A data scientist can then model its long-term performance, ensuring it will last for decades. By systematically breaking down the silos between physics, biology, and computer science, these hidden laboratories are accelerating toward a new paradigm of integrated systems. They are building devices that leverage the very best of each domain, creating a whole that is far greater than the sum of its parts. This collaborative spirit is the true engine of the revolution, proving that the future of power will be built not by specialists working in isolation, but by polymaths working in concert. Our journey ends not with a loud finale, but with the profound quiet of a future reimagined. We have ventured inside the hidden laboratories where motionless power is no longer a dream, but an emerging reality, a silent force harvested directly from the world around us. This is a future built not on extraction and combustion, but on elegant conversion, turning ambient heat, subtle vibrations, and unseen electromagnetic fields into a constant, clean stream of electricity. From the bizarre rules of quantum tunneling to the real-world success of a subway station powered by footsteps, these innovations chart a path away from our reliance on finite resources and toward a dramatically lighter environmental footprint. The challenges of scaling up and seamlessly integrating this new energy layer into our lives are real, but the progress is undeniable. Each day, researchers push the boundaries a little further, inching us closer to a new energy paradigm where power is as ubiquitous and unobtrusive as the air we breathe. How might these silent generators reshape your own community, turning a city bridge or even your daily commute into a source of clean power? What kind of world becomes possible when our devices and infrastructure sustain themselves? We would love to hear your vision for this future in the comments below. If you enjoyed this glimpse into the technologies quietly reshaping our world, be sure to subscribe for more journeys to the frontiers of innovation.